Good day, everyone. We are from Group 5 and we would like to discuss about our report considering engineered nanomaterials. But before that, let us introduce ourselves first. I'm Jomero Levar together with Kenneth Maybuena, Jayat Advitkula, Enzo Suarez, and Eugene Dave Alvarez. And for our table of contents, it contains introduction to ENMs, types of ENMs, applications of ENMs, toxicity of ENMs, safety hazard in handling ENMs, advantages and disadvantages of ENMs, and also the summary. First, let me discuss to all of you about the introduction to engineered nanomaterials. What are nanomaterials? Nanomaterials is one-dimensional material that stands at a nanoscale between 1 to 100 nanometers. That is 100,000 times smaller than the width of a human hair. Nano is a prefix derived from the Greek word dwarf. Nanomaterials can also be classified into naturally occurring, incidental, bio-inspired, and engineered, or what we call engineered nanomaterials, which are our main topic. So, what are engineered nanomaterials? It is man-made or manufactured materials because it has purpose and having particles or constituents of nanoscale dimensions. Engineered nanomaterials are fabricated in the laboratory or industry to obtain materials with specific features and artificially produced and designed with very specific properties related to their shape, size, surface, and chemistry. Nanomaterials are increasingly essential materials in a wide range of fields and industry due to their extremely small size and shape-related properties. By developing nanomaterials, nanoengineering brings new opportunities for progress in healthcare, energy, environmental protection, construction, agriculture, food processing, and other fields. Scientists believe that nanoparticles and nanostructured materials emerged from meteorites during the Big Bang event, which resulted in the development of the universe and Earth. These nanomaterials have been produced and employed by humans since prehistoric times. Because of improvements in nanomaterials, it is now allowed to better analyze all nanomaterial kinds, study their origins in Earth systems, and predict their long-term consequences on the Earth's environment and human health. So next, we are discussing about the types of engineered nanomaterials.
Types of nano-engineered material. First is carbon-based nanomaterials. Second is metal-based nanomaterials. Third is dendrimers. Fourth is nanocomposite. First is carbon-based nanomaterials. Carbon nanomaterials are an extensive family of carbon allotropes consisting of zero-dimensional fullerenes and quantum dots, one-dimensional carbon nanotubes or CNTs, two-dimensional graphene, and three-dimensional nanodiamonds and nanohorns. Carbon-based nanomaterials are intentionally produced fullerenes. This includes carbon nanotubes and buckyballs. Carbon nanotubes are often produced using a process called carbon-assisted vapor deposition. In this process, scientists establish a substrate or a base material where the nanotubes grow. Silicon is a common substrate. Then, a catalyst helps the chemical reaction that grows the nanotubes. Iron is a common catalyst. Finally, the process requires a heated gas blown over the substrate and catalyst. The gas contains the carbon that grows into nanotubes. Second is metal-based nanomaterials. Metal nanomaterials are submicron scale entities made of pure metals. Example is gold, platinum, silver, titanium, zinc, cerium, iron, and thallium. Or their compounds like oxide, hydroxides, sulfides, phosphates, fluorides, and chlorides. Metal-based nanomaterials include gold nanoparticles and quantum dots. Quantum dots are synthesized using different methods. In one method, Small crystals of two different elements are formed under high temperatures. By controlling the temperatures and other conditions, the size of the nanometers scale crystals can be carefully controlled. The size is what determines the fluorescence color. These nanocrystals are quantum dots, tiny semiconductors and suspended in a solution. Third is dendrimers. Dendrimers are highly defined artificial macromolecules which are characterized by a combination of a high number of functional groups and a compact molecular structures. Dendrimers are complex nanoparticles built from linked branch units. Each has three sections, a core, an inner shells, and an outer shells. In addition, each dendrimer has branch ends. Each part of a dendrimer, its core, inner shells, and outer shells, and branch ends can be designed to perform a specific chemical function. Dendrimers can be fabricated either from the core outward or divergent method or from the outer shell inward or convergent method. Like packables and some other nanomaterials, dendrimers have strong cage-like cavities in their structures. Scientists and researchers are experimenting with dendrimers as multifunctional drug delivery methods. A single dendrimer, for example, may deliver a drug to a specific cells and also trace that drug's impact on the surrounding tissue. Fourth is a nanocomposites. A nanocomposite is a multi-phase material in which, in contrast to microcomposites, one of the phases has one, two, or three dimensions of less than 100 nm. The composite spaces have nanoscale distances between them. Nanocomposites combine nanomaterials with other nanomaterials or with larger bulk materials. There are three main types of nanocomposites: nanoceramic matrix composites or NCMCs, metal second is metal matrix composites or MMCs. Third is and last is polymer matrix composites or PMCs. NCMCs, sometimes called nanoclays, are often used to coat packing materials. They strengthen the material's heat resistance and flame retardant properties. MMCs are stronger and lighter than bulk metals. MMCs may be used to reduce heat in computer server farms or build vehicles light enough to airlift. Last is industrial plastic are often composed of PMCs. One promising area of nanomedical research is creating PMC, tissue scaffolding. Tissue scaffolds are nanostructures that provide a frame around which tissue, such as an organ or skin, can be grown. This could revolutionize this could revolutionize the treatment of injuries and organ losses.
Application of engineered nanomaterials. Engineered nanomaterials are found in many products that we use every day. Because of their sizes, they have interesting properties in many applications. Here, I will be discussing some of it. The first one is the applications of nanomaterials in electronics. Nanomaterials can be used to improve the performance of electronic devices such as transistors, sensors, and displays. For example, carbon nanotubes can be used as a replacement for silicons in transistors, while quantum dots can be used to produce brighter and more efficient displays. Carbon nanotubes, also called bucket tubes, is a hollow tube made up of carbon nanoscale diameter. A quantum dot is a nanometer-sized semiconductor particle, traditionally with a coarse shell structure. Quantum dots are widely used for their unique optical properties as they emit light of specific wavelengths if energy is applied to them. These wavelengths of lights can be accurately tuned by changing various properties of the particle, including shape, material composition, and size. The second one is the application of nanomaterials in medicine. Nanoparticles can be used in medicine for targeted drug delivery, imaging, and diagnostics. For example, gold nanoparticles can be used to target and destroy cancer cells, while iron oxide nanoparticles can be used for magnetic resonance imaging or MRI. Magnetic resonance imaging or MRI is one of the most powerful techniques in medical imaging due to non-invasiveness and radiation-free nature. In recent decades, several types of contrast agents have been developed to improve the MRI sensitivity and enhance the information present in the images, namely by using magnetic ions and magnetic nanoparticles. The third one is the application of nanomaterials in paints and building materials. Nanomaterials are used in paints and coatings to improve durability and to provide new functionalities. Currently, the most relevant nanomaterials for the paints and coating industry are nanoscale titanium dioxide and silicon dioxide. Nanotitanium dioxide is used in coatings mainly to exploit its photocatalytic activity, which results in self-cleaning surfaces. The addition of synthetic amorphous silica can improve the hardness, abrasion, scratch, and weather resistance of paint. In addition, nanosized silver, zinc oxide, aluminum oxide, cerium dioxide, copper oxide, and magnesium oxide are currently under investigation for possible future use in paints. The fourth one is the application of nanomaterials in cosmetics. Nanomaterials are being used in cosmetics to keep our skin more youthful and provide protection from harmful sunlight. For example, in sunscreen, skin creams, and in skincare lotions. Sunscreen uses zinc oxide nanoparticles to block ultraviolet rays while minimizing the white coating on the skin. Sunscreen uses nanoparticles generated by ivy plants. Research has shown that these ivy nanoparticles are more effective than oxide nanoparticles in blocking ultraviolet rays. Skin creams use proteins derived from stem cells to prevent aging of the skin. These proteins are encapsulated in liposomes nanoparticles which merge with the membranes of skin cells to allow delivery of the proteins. And last, the skincare lotion in which nutrients are encapsulated in nanoparticles suspended in a liquid, making up a nanoemulsion. The small size of nanoparticles compared to the particles in conventional emulsions allows the nanoparticles to penetrate deeper into the skin, delivering the nutrients to more layers of the skin cells. The fifth one, applications of nanomaterials in pollution control applications. Nanomaterials can be used to remediate polluted environments, for example, by removing contaminants from water and air. Nanoparticles can be used to break down organic pollutants and remove heavy metals from contaminated soils. Air pollution can be controlled with nanoabsorptive materials, nanocatalysis, and nanofilters. For water pollution, nanofiltration, and nanosorbents techniques are used. The application of nanoabsorbent materials is a growing solution to solving this environmental problem. The unique physical and chemical properties of nanoabsorbents enhance their application due to its higher ranking status and quality are beneficial in different fields compared to traditional absorbents. Nanofiltration is a filtration process using nanoporous membrane that is used in waters with low total dissolved solids. The purpose is to remove polyvalent ions and addition to disinfecting it by retaining organic matters. And the sixth, application of nanomaterials in energy. Nanomaterials can be used to improve energy efficiency and reduce environmental impact. For example, nanomaterials can be used to improve the performance of solar cells and reduce the cost of energy storage.
Good day everyone. I will talk about the toxicity of engineered nanomaterials. As a result of their potential toxicity, nanomaterials cannot be completely avoided because of their toxicity, and little known about the information and health and safety implications of exposure to the nanomaterials. The safety of these nanomaterials for the environment and human health has come under scrutiny due to their expanding use, soluble, permeable to biological membranes, or even persistence in the body. Nanomaterials are more likely to be toxic than bulk materials, inducing respiratory tract inflammation and subsequent tissue damage is their main toxic effect. Engineered nanomaterials released into water bodies can raise freshwaters and marine species by causing declines in their vital functions like growth and reproduction. Nanomaterials have shown potential for technological and medical applications, but their toxicity has raised concerns about their safety for the environment and human health. If nanomaterials get into the soil, they can contaminate and migrate into surface and groundwaters. Wind or rainwater runoff can also transport particles to aquatic systems from solid waste. Wastewater effluents, direct discharges, or unintentional spillage. The toxicity of nanomaterials is affected by their type, surface geometry, diameter, length, and function. Nanomaterials exposure can occur through inhalation, skin contact, unintentional injection, or ingestion. Ultrafine particle inhalation has long been known to have respiratory and cardiovascular consequences, and inhalation is a primary focus for exposure, evaluation, and control. A substantial body of information has been produced as a result of research and field and laboratory studies. The hazard identification. Engineered nanomaterials with novel sizes, shapes, and chemical properties may be exposed to workers in industries related to nanotechnology, necessitating further study. The effects of engineered nanomaterials exposure on target organs and those distals to the site of uptake. It is not always possible to predict engineered nanomaterials toxicity from the unknown effects of engineered nanomaterials components or from the toxicity of ultrafine materials and ENMS. To describe the pertinent exposures factor for dosage, durations, and route, further research is required. The engineered nanomaterials exposures effects in the lung. Because of their size, shape, surface, functionalization, solubility, surface, reactivity, association with biological proteins, binding to receptors, and propensity to aggregate, ENMS are more biologically active and have higher uptake. The engineered nanomaterials exposures effects seen in the brain. By generating H2O2 and superoxide radicals and hyperpolarizing mitochondrial membrane potential, metal oxide ENMS can cause neurotoxicity. The injections of Syria intravenously to rat affected brain oxidative stress markers and antioxidants enzymes. The engineered nanomaterials exposures effects seen in the skin. Metal oxides ENMS, like silver ENMS, can cause dermatotoxicity by reducing the viability of human epidermal keratinocytes. The summary of the effects of engineered nanomaterials exposures on target organs and those distal to the site of uptake. Due to the push to reduce whole animal research, cell-based or in vitro models of the entire organisms are predicted. Other model organisms such as ecotoxicological and developmental biology research have employed elegans and zebrafish. The clearance of engineered nanomaterials, their translocations to distal sites, and persistence. The simple info of engineered nanomaterials clearance and translocations from the original sites of exposure to distal locations comes from whole animal studies. Engineered nanomaterials have been shown through translocates after inhalations and injections with polyurine distributions into the fetus and titania accumulations in the testes and brain. Although ENMS can deliver drugs to the brain, There are worries about their effects due to their persistence. 50 nm non-ionic polystyrene (ANMS) were discovered in the liver, spleen, and mesenteric lymphatic tissues 10 days after oral dosing. Studies have found that MWCNT cause fibrosis and inflammations of the lungs. The psychochemical properties of engineered nanomaterials that impact their hazards, the role of surface coating in engineered nanomaterials effects. Surface coating have an impact on engineered nanomaterials, psychochemical and biological characteristics, but it is unknown how they will affect human health, making it difficult to predict how toxic engineered nanomaterials will be. The effects of engineered nanomaterials at distant sites. Engineered nanomaterials induce hepatotoxicity, mitochondrial DNA damage, atherosclerosis, disrupted aortic mitochondrial homeostasis, accelerated atherogenesis, increased serum inflammatory proteins, blood coagulation, and increased plasminogen activator inhibitor. The hazards assessments from fire and explosions of engineered nanomaterials. The engineered nanomaterials are highly reactive in catalytic reactions. They increase the risk of fire and explosions. The exposures assessments. The nanoparticle emissions assessments technique, or the NEAT, was developed by NIOSH to evaluate airborne engineered nanomaterials, which have been linked to two deaths among female employees aged 18 to 47. As a student of engineering, I want to take this opportunity to remind you all how crucial toxicological research and risk evaluations of nanomaterials are to lessen the possibility of negative effects on human health and the environment. It is crucial to use a safety by design approach when creating nanomaterials.
Safety hazard in handling engineered nanomaterials. Control measures can be implemented using the hierarchy of control principles. First, try to eliminate the exposure. If you are unable to eliminate the exposure, then engineering solutions should be investigated, including ventilation and source enclosures. The National Institute or Occupational Safety and Health or NIOSH states that current knowledge indicates that a well-designed exhaust ventilation system with a high efficiency particulate air or HEPA filter should effectively remove nanomaterials. The National Institute for Occupational Safety and Health, or NIOSH, is the lead federal agency for research on the occupational safety and health implications of nanomaterials. In this role, NIOSH recognizes that the research community is at the front line of creating new nanomaterials, testing their usefulness in a variety of applications, and determining their toxicological and environmental impacts. Although the risks of nanomaterials to human health and the environment are largely unknown, it is prudent to be aware of current informations and recommendations for handling nanomaterials from NIOSH and other authoritative sources. Education and training in safe handling is essential. Separate eating rooms and change facilities are good options, while personal protective equipment or PPE is being studied to determine if current models offer adequate protection from nanomaterials. Use of such equipment can be considered as a part of a complete health and safety risk management program. When any PPE is used, it should be done so as part of a complete PPE program. Health monitoring may also be considered. PPE is a barrier to protect the body and prevent the leakage of particles. Hygiene. Do not consume or store food and beverages or apply cosmetics where chemicals or nanomaterials are used or stored, since this practice increases the likelihood of exposure by ingestion. Do not use mouth suction for pipetting or siphoning. Wash hands frequently to minimize potential chemical or nanoparticle exposure through ingestion and dermal contact. And remove gloves when leaving the laboratory so as not to contaminate doorknobs or when handling common use objects such as phones, multi-user computers, or etc. Next, engineering controls. Use gloves, glove boxes, fume hoods, or other containment or exhausted enclosures when there is a potential for aerosolization such as handling powders, creating nanoparticles in gas phase, pouring or mixing liquid media which involves a high degree of agitations. Do not use horizontal laminar flow hoods, clean benches, as this device direct the airflow towards the worker. Use fume hoods or other local exhaust device to exhaust tube furnaces and or chemical reaction vessels. Perform any maintenance activities such as repair through equipment used to create nanomaterials or cleaning replacement of dust collection system in fume hoods or under appropriate local exhausts, and thus recognize hazard and assess risk. Be sure to consider the hazards of precursor materials in evaluating process hazards such as acidity, basicity, oxidizing or reducing strength, and flammability performed through hazard assessment and risk assessment for the nanomaterial synthesis. And consideration should also be given to the high reactivity of some ultrafine powdery materials which possess potential fire and explosion hazards. And last, evaluate nanomaterial transfer methods, temperature controls, and other process controls.
Advantages and disadvantages of engineered nanomaterials. Advantages: can generate energies such as solar panels more efficient and cost effective. They can also open up in new ways in which to both harness and store energy. Set to introduce a number of advantages in the electronics and computing industry. This is where their use will permit an increase in the accuracy of the construction of electronic circuits on an atomic level, assisting in the development of numerous electronics products. Very useful in medical field, which permits the bonding of cells and active ingredients. This will result in the obvious advantage of an increase in the likelihood of successfully combating various diseases. High porosity, which again increases demand for their use in a multitude of industries. Disadvantages: not a large amount of information on the health and safety aspects of exposure. Due to the relative novelty of the widespread use of nanomaterials, there is not a large amount of information on health and safety aspects of exposure to the materials. Inhalation exposure, the results of which has suggested that nanomaterials such as carbon nanotubes and nanofibers may cause detrimental pulmonary effects such as pulmonary fibrosis. Knowledge gaps regarding nanomaterials, meaning the manufacturing process can be complex and difficult and the overall process is also expensive, requiring optimum results, especially regarding their use in consumer goods in order to avoid financial loss. Risk of ending up in a aquatic ecosystems. Cosmetics such as sunscreen, which we apply to the skin, can run the risk after they are washed off. Nanomaterials that have been engineered may also end up in water bodies such as lakes and rivers. Although the concentrations of these engineered nanomaterials is expected to be quite small, repeated release may cause the concentrations to increase over time, exacerbating the related negative effects. Summary. Now for our summary, we have the engineered nanomaterials is a chemical substance or material that is engineered with particle sizes between 1 to 100 nanometers in at least one dimension. Engineered nanomaterials has four main types, which is the carbon-based nanomaterials, metal-based nanomaterials, dendrimers, and the nanocomposites. Carbon-based nanomaterials are often produced using a process assist, called carbon-assisted vapor deposition. Gold nanoparticles and quantum dots are part of metal-based nanomaterials. By controlling the temperature and other conditions, the size of the nanometer scale crystals can be carefully controlled. Dendrimers has three sections: a core, an inner shell, and an outer shell that can be designed to perform a specific chemical function. Nanocomposites combine nanomaterials with other nanomaterials. The three main types of nanocomposites are nanoceramic matrix composites, metal matrix composites, and polymer matrix composites. Engineered nanomaterials can be found in many products we use every day. It can be used in improving the performance of electronic devices such as transistors, sensors, displays, and etc. Nanoparticles can be used in medicines for targeting drug delivery, imaging, and diagnostic. Paints and building materials to improve the durability and to provide new functionalities. Cosmetics to keep our skin more youthful and provide protection from harmful sunlight, and the good example here is the sunscreen. Pollution control applications to remove the contaminants from water and air, and energy to improve the energy efficiency and reduce the environmental impact. There are also toxicity in the engineered nanomaterials where the novel sizes, shapes, and chemical properties may be exposed to workers in industries related to nanotechnology. The other are the effects of ENM or engineered nanomaterial exposure on target organs and those distal to the site of uptake, and examples of that is the exposure in the lung, seen in the brain, seen in the skin. There are also the clearance of ENMs, their translocation to the distal sites and persistence, the psychochemical properties of ENMs that impact their hazard, the effects of ENMs at distal sites, hazard assessment from fire and explosion of ENMs, and exposure assessment. Of course, there are safety hazards in handling engineering nanomaterials, like in a hygienic way, for example, is do not use mouth suction for pipetting or siphoning, and wash hands frequently to minimize the potential chemical or nanoparticle exposure. There are also engineering controls like handling powders, creating nanoparticles in a gas phase, using fume hoods or other local exhaust devices to exhaust the tube, furnaces, and etc. And there are also recognized hazards and assessed risks that need to be sure to consider the hazards of precursor materials in evaluating process hazards such as acidity, basicity, and oxidizing, and flammability. And that's all for our reporting. Thank you everyone for listening, and have a good day.